discrete time systems. So last two lectures, we talked about characterizing discrete time signals, both their representation and their characterization. Today, we're going to do them not for the signals, the nouns, the data, but this time we're going to do them for the systems, the verbs, the things that change stuff around. That's much more interesting. We're going to talk about how to represent them, and we're going to talk about how to characterize them. So you'll remember how we represented different kinds of discrete time signals. We did it using formulae, we did it using stem plots. Discrete time systems also have several ways that we can represent them. Remember, in the big picture we're talking about, this is our signal, this is our system, and this is our resulting signal. So we're talking about different ways to represent what this is. The first is an equation. In fact, we're going to call it a difference equation, and that may or may not be unique. Now, a difference equation is to discrete time what a differential equation is to continuous time. So it's easiest, I think, to show this with an example. I'm going to talk about an accumulator. An accumulator has an output that's equal to the sum of all the inputs, starting at negative infinity all the way up to n. So in other words, it just accumulates whatever comes in. And another way that we could represent that more compactly would be as the sum from k equals minus infinity up to n of x of k. This is one example of a difference equation. And now using just a little bit of algebra, I'm going to manipulate it into a much shorter one. Well, this already is shorter, but what if instead we broke out that last part? So we said we're going to only add up all of them up until the very last one, and then I'm going to separately add the last one. So in other words, the first part of this is equal to this section, and then the last section, so that's this, and then our last section, we just write down without any changes. You might see where we're going with this. There's one last trick. Take a look at this, the sum from negative infinity to n minus 1, and realize that's exactly what this is for n minus 1. If you plug an n minus 1 in here, this is what you get, this is what you're left with. So that's the same thing as this. And now we could write it almost like a differential equation. And so here's two different ways we can write the exact same difference equation describing what this accumulator does. This is an integrator. This is a discrete time integrator.
I just missed that part where you went from that second summation to the y of n minus 1, if
Sure.
you don't mind.
Let's just plug in here what happens. You know, I could put in y of dog, right? And then I'd get x of minus infinity plus all the way up to x of dog. So instead of dog, I'm going to put in y of n minus 1. So now I've got x of infinity plus all the way up to x of n minus 1. But if you realize this is the exact same thing as that. So therefore, I can rewrite this whole part as this. And then the last part doesn't change. Make sense? Excellent. You'll see that kind of trick done a lot in DSP. So math equations are nice, but block diagrams are often better. They just sort of intuitively show you what you're doing. So here's a block diagram example. What stem plots are to discrete time signals, block diagrams are to discrete time systems. So we've got x of n, and it goes through a summer, and here's a delay element, and it goes back to the summer. If you want to see what this does, you can kind of imagine that as your input comes in, it always gets summed up, and that's your output. Well, that in a picture is the exact same thing as what your accumulator is. Another way to show what an accumulator does. As an example of this in real life, you can have a moving average filter, much like you did with the first homework problem when you evened out the bumps in the EKG caused by picked up noise. This might look something like y of n equals x of n minus 2 plus x of n minus 1 plus x of n, all divided by 3. So as an example of that particular one, that's a little, this one starts summing up x from n equals minus infinity, but to get something like this, this will be our x of n, and I'm going to divide it by 1/3 at the end. And then we're going to have to delay that by 1, and I'm going to delay it the delayed version by another one. So this will be delayed by 2. And that's a block diagram of a length 3 moving average filter.
And so, sir, those will never really be like z to the negative 2 to show going back twice. You'll just have one go into another.
You could equivalently, sure. Is this your question? Couldn't you do this as well?
Yeah.
Yeah, that's perfectly correct. It's just a little bit more complicated to draw. And this tends, and the one on the left tends to be the way you'd actually program it on a chip. You'd end up having a buffer, a first in, first out buffer, just a shift register. And this, you can almost kind of see it's going to be a length 2 shift registers with 2 taps on it. But there's nothing wrong with this either. Let me show you when you'd actually use a moving average filter, another example of it.
Sir, what does the delay do? The
Delay,
one?
you'll remember from one of our earlier lectures that delay, if you plug in x of n into a delay, what you get out is going to be x of n minus 1. So if you plug in a stem like that into a delay, where it's all zeros before, what you get out is, here's your 0 element. And now 1, 2, 3, you're going to get your. So it's the same thing as you put in, just delayed by 1. Let me give an example of when you actually can see this, of when this is actually used. Say you had a, and by the way, these are the only 2 common ways that discrete time systems are represented. It's either as an equation or as a block diagram. It's one of these 2. Say you had a system. Say you had a anti-tank system. You've got this tank that's rolling around, and if you've ever seen actual tank battles, holy cow, there is dust galore. It's not that they're even trying to put up smoke screens, but these treads just churn up ground. And you've got a high-speed anti-tank weapon that's got some DSP processing in it, and it's got a sonar in the front, and it will only explode when it gets in the vicinity of the tank. We have a projectile sensor, I'm going to call it S of N. So this is what the sensor is receiving. And it would really like to look something like this. It's not receiving anything, and then all of a sudden, like a U of T, it's the tank is detected here. Problem is that that ideal signal is going to be corrupted by D of N, which is your dust noise. And the dust noise is going to be kind of random. It's going to be all over the place, and it's hard to predict what it will be. And so you're going to take that received signal, and you're going to put it through. You're going to sample it quickly. You can sample it very quickly because these dust motes are very small. You go through them very quickly. Here's an example of a 4, 1, 2, 3, 4 moving average filter. So divide it by 4. And here's your process signal P of N. Okay, so as a quick MATLAB demonstration of this, here's our projectile signal. If there was no noise, no dust signal, when we add the dust signal in, this is actual data that was computed on the fly. This is our signal up here, a U of N, to which I've added additive white Gaussian noise. And you can see in the general on the right, it's higher than on the left, but you'd be hard pressed to say exactly when to pull the trigger and have your round explode. If you put it through that moving average filter that I just showed, this is the actual data again. Now it's pretty clear that these random data, half the time will be high, half the time will be low. So when you process it, now you could create a threshold at say the 0.5 level and be far more confident that you're actually going to detonate it at the right location. If you put the threshold 0.5 level over here, you'd pre-detonate because of noise. Questions on that?